is I want to talk about multi-objective linear programming.
So multi-objective linear programming. This is a vast subject. There's a lot we can do here. So essentially it comes down to one line in the section in the book I asked you to read. We want to compare apples and oranges. We cannot compare apples and oranges unless we have some way of putting them on the same scale. So there was some discussion here earlier about units in Chem 151, and so we want to have things in the same units. So what was the very first linear programming problem we attacked in this course? What was the first one we did?
Like iron.
Yeah, the diet problem. So we developed the theory completely here for the diet problem. We showed how to find optimal solution. Are you happy with the optimal solution? Are you happy with the method we used to solve the diet problem? Are you happy with what we optimized? No. I had a group, I've got to be very careful because this is being recorded, when I taught a senior seminar version of this a couple of years ago that tried to figure out, well, what is the cheapest diet possible that will keep you alive that's available through Stop & Shop's Peapod. So they actually wrote some script programs to download all the information from Stop & Shop's web pages. It was truly impressive, and they brought the stuff to class for me to eat. Fortunately, I was on medication, and as I was able to claim, I don't know what this food would do to me, and I cannot eat it because it might have a bad effect with my medicine. It was not appealing. I will show you a picture of what the cheapest meal that will keep you alive looks like. No, we were not able to get up to spam. It was below the level of spam. It was really bad. It would keep you alive, but it would not be living. Okay? So you are not going to be in a situation where, for the most part, you only care about one object. You want to care about many different things. So for the diet problem, in honor of a great movie, Staying Alive, right? That's extremely important. That's something we definitely care about. What else might we care about? Variety. I feel like Family Feud right now. And so for me, I'd put variety as number 3. For some people, variety is important. When I was in grad school, we made pasta, and that lasted us for a couple of days. Then we made chicken, and that lasted us for a couple of days, and then we repeated. But some people actually prefer variety. Cost. Yes. Taste. So would you put taste actually above or below variety?
Put it above cost, honestly.
Above cost. Okay. So here. We'll say now it's unordered. Anything else you might care about?
Nutrition, possibly.
I mean, that should be in the staying alive.
I don't know if this would be multi-objective or integer, but what if you have different combinations of food that you like you want to have together, you don't want to have together?
I would put that under taste.
Would that be different though, the same structure?
I think it would be related to the general thing about taste. Is, certain foods go together well. I mean, I guess you could. All right. Well, any Star Trek fans here? Star Trek Deep Space Nine? There was an episode in Star Trek Deep Space Nine where there was a hitman assigned to kill somebody. And he was masquerading as a fragrance salesman. And he had different fragrances. And if you combined a couple of them, it became a bomb and would explode and kill someone. And so individually, each one was fine, but if you combined them. So if you want, I will view your thing in light like that maybe if I eat these foods together, there'll be some bad reaction inside me.
Preparation time?
Preparation time, oh, I like that. So I'm Jewish, Passover is coming up in a few months. What are Jews supposed to not do during Passover? Right, and why don't Jews eat leavened bread during Passover? There was no time to have the bread rise. But Jews will spend 4 to 6 hours cooking elaborate meals, and that's considered acceptable. I have argued for years that the proper way to celebrate Passover is all food must be cooked in 18 minutes or less. I have yet to find a rabbi to agree to that.
Longevity, like how long the food will last.
Okay. All right, we'll do maybe one more or two more. Okay.
Whether or not a food is organic or locally grown.
Okay. And in fact, what's nice about the organic is this could be related to keeping the suppliers in business. So if you don't spend a certain amount of money on locally grown food, then they may go out of business.
Yeah, I was going to say something like that, like availability. You want to get things within a certain radius. Like, say you want to walk to the grocery store instead of driving all the time.
Right? David?
How is the food relative to what you get in Spring Street?
I'm sorry?
How is the food relative to what you get on Spring Street?
I'm sorry, what do you mean by that?
In terms of cost and quality, because if, let's say a meal swipe is costing you 7.5, but for 7.5 you can get something better than what you get in Driscoll.
Right, so the question is, do you have a fixed cost? When I was at Yale, I was there during a dining hall strike. And so Yale refunded our meal plan money. And we found that we could actually eat out for every meal for less. Morally, we felt it was wrong to kick back some of the money to the striking workers to keep the strike going. But it was actually in our interest to keep the strike going. So, can you give me a one-word summary of that? All right, politics.
I do want to plug for nutrition just because a diet that is optimal for, say, if you're a weightlifter,
Okay.
will not be optimal for, say, if you want to maximize your own longevity. Likewise, a diet that allows you to stay alive in the short term won't necessarily maximize your lifespan in general.
Okay, that's definitely a reasonable point to add. All right, the list could go on much, much longer. It would be an interesting experiment to actually have a bunch of us assign weights to this. And this is very similar to what I want to do for the Math Blast people. So who are the Math Blast people here? Okay, so one of the things that I think you might want to do is say you've got 100 points to spend and you want to assign them to the different things. So you can almost do a bullet vote. I really want to go to this talk. And then you might be able to then force that preference, but then maybe that's not fair because then the system will give you extra credit, so you might want to put some caps. So for something like this, we need to come up with different weights. Is there anything here that is not a luxury?
Staying alive.
Yes. All right, staying alive is not a luxury. Right? That one is not one of the things that we get to choose. That must be done. This must be in the constraints. Cost, variety, taste, all these other things, these are luxuries. Once you have a diet that keeps you alive, then you can start thinking about these other things. And so the way multi-objective programming works, or at least a very simple way of doing this, is to say you have some weights, W1 through Wn are weights. 0 less than equal to Wi less than equal to 1, W1 plus Wn equals 1. So we have a bunch of non-negative numbers that sum to 1. And then what we can do is we have C1 transpose x1. We multiply that by the weight 1. And then weight n, Cn transpose x. Oh, so this is not x n or x1, that's just x. So we have different objective functions. This is the first objective function. This is the last objective function. We take a linear combination of them. Does it matter that the weights sum to 1? What if the weights sum to 5? Would that make any difference? No. As long as we assume the weights are non-negative, it makes no difference. Why might we want to assume the weights sum to 1? Yeah, the probabilities, that could be a way of maybe talking about putting them all in a natural scale so you can compare how much is this worth to you relative to something else. It's really the ratio of the weights that matter, or the ratio of a given weight to the total weight. So you might look at Wi divided by W1 plus Wn. How many people have seen formulas like this in economics? So if you've taken some econ classes, you'll see things like this in valuation theory, in terms of how much a good is worth to you. So again, I really don't care that they sum to 1. In fact, I really don't even care that they're less than or equal to 1. I can drop all of those constraints. This is just a nice way to normalize things. Weights are extremely important in mathematics. I'll post some additional comments about where weights occur in analytic number theory, because I can then also use that for the advanced analysis course I'm teaching. But the idea here is you want to compare apples and oranges. So you have to decide how much is cost worth to you over variety. What is the trade-off you're willing to make? And so typically, it may not be very easy, but there should be some extremes. Are you willing to spend an extra 10 cents for a great variety out of a $100 grocery bill? Or to get a much better taste? When I was at Yale, hypothetically, we might have found a storage facility for the dining hall, and we might have seen that the meat was marked grade D, and they actually had the words on it, fit for human consumption. They, I think, had to put on the box that it is legally admissible to serve this to people. The food got better in my time there, but it was bad for a while. For a small amount of money, you're definitely willing to do that. Are you willing to double your grocery bill? At some point it becomes clear, I'm not willing to go to that extreme. But the small extremes, the trade-offs, this is very hard. This is a huge problem in so many different things. So can anybody give me a situation where you would be trying to figure out these different trade-offs? Where might you have a problem like this? Yes?
You might like the taste of something more, but it's not organic.
Okay. Okay, so this is all going back to the diet problem. I want to drop the diet problem. Where in your life have you had something like this? And I think everybody in this room has had to face this at least once in the last 3 or 4 years. Yes?
Well, last night was housing draw for juniors, so you have to balance out, is it worth living in poker and having to walk 20 minutes to science class, but getting your common room with friends?
Yeah. So if people want to do, instead of doing standard homework problems in the future, I'm happy to trade homework problems for doing something for housing draw to improve housing draw. So if people want to make any trades like that. When you do housing draw, is everybody considered equal? Wait. Discrimination exists on campus? Isn't that violating the 13th, 14th, and 15th Amendments to the US Constitution? Oh wait, we're a private college. Never mind, we can do that. How are we allowed to discriminate? Can we discriminate amongst right-handed people? People with brown hair, blue hair? What can we discriminate on the basis of? Age. Age discrimination is acceptable.
And gender, actually.
And gender.
Yeah, you can gender count that.
Yep. So there's certain levels of discrimination that is acceptable. Now, fortunately, the age discrimination should balance out over time. Everybody should be discriminated equally in each year. But there are different systems in which you could award different points for being a senior, a junior, a sophomore. When you have a team of several people trying to pull into a room together, let's say you have 4 seniors, 2 juniors, and 1 sophomore. Actually here, we normally do things of, I think, 6. Is this an acceptable block to go for a room?
Yeah.
How do you weight this?
Well, they actually have a weighting system.
They have a weighting system.
It's 4 points first.
So you give a certain number of points for each senior, then a small number of points for juniors, then a small number of points of sophomores. If you change those weights, that can affect things. How do you set those weights? I'm sorry?
Arbitrarily.
Hopefully it's not entirely arbitrarily, right? But you want some system to come up with reasonable weights. And the system should basically give preference to the seniors. And then the sophomores who don't know better, you can kind of... But this is one area that is extremely ripe for research, is trying to figure out what is the proper weights for something like this. Right now we're using linear weights. Each senior is worth the same amount.
Not necessarily.
No. Oh.
If you were a J or a housing coordinator, you get more points
Okay. Okay.
This year's
Good thing. No, that's fine. It's not been recorded, so nothing was spilled in conference. If we take non-special people, generic Williams students who are not affiliated in any way, shape, or form with things that could bump up, you would just take however many points you have per senior and multiply by 3. And however many juniors you have. And so the more juniors you have, you keep getting the same hit in terms of loss of points from seniors. You could actually have things change so that maybe it's not weighted equally. All right, so just housing draw is one situation where you would want to put in some kind of multi-objective linear programming, and the difficulty is choosing the weights. What's another situation, we'll just do one more and then move on, where you've all seen the fact that you have to take into account weights between different alternatives as to what really matters to you. Yes?
The fact that we're taking a bunch of classes and we have limited time, so...
You're taking a bunch of classes, you have limited times. Other things you could do, so we'll do classes, your college. I'll risk putting this one up here. So if you do not understand that you do have to put in weights and cannot do everything at once, but when you're choosing where to go for college, do you want a big city campus? Do you want a small liberal arts college? Those may not be compatible. Now there are some liberal arts colleges, and you've got to decide how much these things are worth. So this idea of trying to solve problems with weights is extremely important. It's an extremely rich subject. And the question can become, what's the most efficient way to do all this? All right, what I want to do now is move on to quadratic programming. What's nice is it's very easy to introduce the weights in terms of what we've done. As long as we're using linear weights, it's not a problem. The difficulty would be is if we had quadratic weights, if we didn't count all the costs equally. So over here, so now this is quadratic programming. And I've deliberately not had you read about this because I only want to spend a few minutes on quadratic programming and get you to the point where if you want to learn more, you can read the book, and I'm happy to discuss with you. So in the multi-objective, we had linear weights. We had something of the form the sum of Wi Ci transpose x. I goes from 1 to n. That may not be what we want. We may want to have nonlinear weights. And I've mentioned this in the past. Does anybody know an example where we would want nonlinear weights? It's huge in statistics. It's mentioned early in the book with stars. Yeah. Nope.
When two weights interact with each other?
So one is weights could interact with each other. But there's a really big thing in statistics where it's not linear.
Least squares?
Least squares. How many of you have not seen least squares? It's not a prereq for this course. I'm just curious. How many of you have not seen the method of least squares? Okay. So in the method of least squares, you're trying to minimize the error squared. So basically the sum of observed minus predicted at I squared. Why wouldn't I try to minimize the observed minus predicted? Well, then positive errors can cancel with negative errors. Why don't I use absolute values? The absolute value function is not differentiable. The square function is a really good function to use.
And it also punishes further away observation.
Right, so the question is whether or not you like that. So imagine you are recording your data. Achoo! And you sneeze as you're making your measurements. Okay? Now, because if I'm doing things quadratically, that one bad data point is going to have a huge effect on what's going on here. What should you do with that one data point? You should find some way to justify throwing that out. I'm very proud that I was discarded from a psychology experiment when I was an undergraduate. And they just threw me away as a data point. You would not want to put too much weight on this. But of course, there's always the danger. Maybe this was a good observation. And so you've got to be very careful. If you have something as, we dropped the machine. Or we noticed the battery was out. If you have some reason to justify throwing it out, then you would throw it out. So it's either good or bad that you put extra weight on large deviations. This will tend to smooth things out a little bit. But that may not be the best thing. I actually prefer absolute values if I am farming out the project to someone else to do. If I am doing the project, I prefer to use squares because I can then use calculus. So trying to minimize something like this is extremely important. And the method of least squares, this covers far more than just linear functions where you're doing the best fit straight line. A lot of times you can do a logarithmic change of variable, you can have exponential relations, you can have logarithmic relations. They all fall in the confines. This leads to the subject of regression in statistics. This is extremely important. We can do this in terms of quadratic programming. And I think early in the book they talk about a paper about minimizing, they're trying to calculate, I think, populations of stars in galaxies. And sometimes they get negative populations of stars, which they know is a little bit absurd. And they were able to convert this to a quadratic programming problem. So a lot of times we have situations where we want to have quadratic. We want to have nonlinear terms. And the simplest nonlinear is quadratic. Okay, so we have some choices. So the canonical problem was ax equals b, x is greater than or equal to 0, and we want to C transpose x, we want to minimize this. There's a couple of ways we could make things nonlinear. Where could we introduce the quadraticness? I'm sorry? So we could have quadratic terms in here. We could have the entries of A depend on x. So quadratification. Maybe A depends on x. What else could we do? Cost function. The fact that x has to be greater than or equal to 0, we could say x is greater than or equal to 0 squared, but it doesn't make. One of these is easy to do, it turns out, and one of these is extremely difficult. So I thought about having this as an exam question. I've decided not to have this as a midterm exam question, but to just do it in class right now. And so this is a great example of a type of problem I could ask. If you could handle quadratic A, what would that mean? If you could handle quadratic C, what would that mean? It turns out if you could handle one of them, you can do so much. Far more than you should be able to do. Any thoughts as to which one is beyond our ability? A probably. I'm talking about objective functions that involve squares, the method of least squares. We talk about how we can use that. So it seems like this is in play. So this is beyond us. Now it's very tough to prove why you can't do something. So in mathematics, it's very hard to show you can't do this. Maybe you haven't been clever enough. So cryptography is all based on the fact that there are certain problems which are easy in one direction and are thought to be hard in another. So RSA, which was the gold standard for years in cryptography, is if you take two numbers, is it easy or hard to multiply them? Easy. If you take a number, is it easy or hard to factor it? It seems harder. Nobody knows a good way to factor numbers. There may be and we just haven't discovered it yet. Years ago, there was a system that was being used by some people, and it turns out it was easy to go in the other direction. And the story I heard is that the NSA had known about this for years and just didn't advertise the fact. And then anybody who was using the system, their stuff was at risk. It turns out if we could handle quadratic in here, if we could allow A to have its entries linearly depend on X, something really bad would happen. And we would be able to do something which we think is hard. So it would allow us to do something that we think is hard, and that's why we don't feel that this is doable. Any thoughts as to what we would be able to do if we could handle A's that depend linearly on X? So if can do A's depending linearly on X. Any thoughts as to what that would allow us to do?
Some sort of NP problem.
Yes. Which, traveling salesman. We could do the traveling salesman problem. What does the traveling salesman problem involve? Why is the traveling salesman problem hard? So the traveling salesman problem is you've got a bunch of cities and you want to visit each city once and only once. You want to choose the route of shortest length. Turns out this is extremely hard. You can view this as a scheduling problem. I want to schedule my trip. Why is scheduling problems difficult?
Because each choice depends on all the ones you made before.
There's that, but
There's an exponential number of.
oh, we've got exponential in so many things, but what makes the scheduling problem difficult? We can do a lot of linear programming problems. Why does the scheduling problem not fall within the confines of the simplex method? What makes the scheduling problem difficult? I'm sorry? So think about what was going on. When we were talking about movie theaters, what kind of variables did we have? Discrete, integer valued. That's the difficulty. We need, when we're using the simplex method, we need to be able to have continuity. So simplex method needs continuity. Fails for discrete. And we talk about having our dial and turning it up a small amount. This is why I like, we're finishing up a unit. This is a great way to summarize what we've done and see the connections. The simplex method, it is crucial in terms of understanding how it works that we can move arbitrary amounts. When we have integer valued random variables, we can no longer do that. That doesn't mean the problem can't be done easily. It just means the simplex method won't work. It turns out if we could handle A's that depend linearly on X, we could do the traveling salesman problem. We could do any scheduling problem. We can do any integer programming problem. We can do any binary integer programming problem. Can anybody give me a quadratic constraint that allows me to do binary integer programming? One constraint. It's nonlinear. And if you give me this one quadratic constraint, I can do all of binary integer programming. What is it? Yes? Well, no, because I could take x squared to be 1/2. I could take x to be 1/2 and that would satisfy it.
X squared is equal to x.
Okay, so you want to add x squared equals x. I would phrase it as x, 1 minus x equals 0. Either way is fine. Excellent. Imagine we could include this as a constraint. Is this a linear constraint? It's a quadratic constraint. What does this quadratic constraint do to x? Makes it binary. Okay? This shows you how difficult things can be. It's amazing. If you think back to calculus, the main idea of calculus is the linearization of nonlinear functions. You replace a function with a tangent line, and locally, you say any function is locally looking like a straight line. You get Newton's method, you get lots of great things you can do with that. We have all these linear constraints. If we had something that was fundamentally quadratic, we could use that to force a variable to be integer valued, in fact, to be a binary indicator variable to be 0, 1. As if we could just add quadratic constraints, that would tell us that binary integer programming would be amenable to the simplex method, or amenable to something like that. So to me, this would be an example of a good hard problem that I could put on the exam. And again, looking at this live, this is not an easy thing to quickly see what's going on. But this shows you how difficult the situations can get. When you're trying to get a sense of how far you can push a method, what you wonder is and the computer scientists are wonderful at this, they have a collection of difficult problems, right? And they've given these difficult, I apologize for the CS people for doing a quick bastardization version of it. What do you call these difficult problems? You call these problems NP-hard. And essentially you show that your problem is equivalent to one of these NP-hard problems and is therefore hard. And so what we've just shown here is that if we could handle quadratic constraints, we can handle binary integer programming problems. And since we believe binary integer programming problems are hard, we don't think we can handle quadratic constraints. Now the objective function, however, that's different. We can handle objective function. So again, what I'm trying to do now is I'm trying to give you the broad overview of the subject without going into the nitty-gritty technical details. If you want to read the technical details, look at Chapter 2. And Chapter 2 goes through how to extend the simplex method to a special case. So now we want ax to equal b, we want x to be greater than or equal to 0, and now we want to minimize C transpose x plus x transpose some big matrix C x. And C is a very special matrix. We want C to be a positive definite matrix. And it turns out in this case, the simplex method can be generalized. Very different than putting the quadraticness in the constraints. So again, one of the reasons I want you to go through the proof of the simplex method is now we can talk about this and see why this is reasonable, why this is not. When you think about the simplex method, you think about phase 2. You start off with a basic feasible solution, and then what do? You come up with this new solution y to the dual problem, and you see, is it feasible for the dual problem? If it is, you have an optimal, and if it's not, you keep doing this process. And what do you do if you're not feasible for the dual problem? You do this kind of exchange. You say, okay, I'm not optimal. There's some column that I'm using which is a non-optimal choice. I can do a better job by switching this out for another column. And in fact, the simplex method will tell you, here's a column you should try. It might even tell you, here's a bunch of columns, choose one of these. You then write that column as a linear combination of the others, you swap it out. And because of our non-degeneracy, when we change our variables continuously, there will be one coefficient that suddenly becomes 0, and all the others are non-zero, and now you can make your swap. In all of those arguments, what have we never used? Linearity of the cost function. All we needed to do is show that the cost function was decreasing. We didn't need to use the linearity of the cost function. So again, this is the high level. This is trying to save you going through lots of tedious details and computations. This is the big picture, the bird's eye looking down. That when you're looking at the nuts and the bolts of the simplex method, we did not use the linearity of the cost function. We just used the cost was decreasing. Yes?
But you do need to check that the s component of y is less than or equal
Yes, you need to do some kind of check, but we don't need linearity there.
So if you have, how do you take the cost matrix into that comparison, or is that?
It's getting into too much of the detail. I'm just trying to give the broad overview so that you have a sense of what can be done. Are any of you ever going to do the simplex method by hand? No. Are any of you ever going to do quadratic programming by hand? No. I want you to know what's out there. I want you to know this is a tool. So one of the people who came for the, I think, Goldman Sachs lunch, he got his job from meeting people last year when he was an undergraduate here. He's been doing quadratic programming now. And again, he actually knows the stuff. He knows what's going on. He knows the theory, but he doesn't need to. There's programs that will handle stuff like this. And so it turns out that when we look at the simplex method, a lot of the calculations follow over, but we have to be able to make certain types of comparisons. And it turns out if the nonlinearity is just localized in the objective function, we can generalize these calculations and we can do them. This is not a proof that the simplex method generalizes. This is a first course in operations research. There's a lot to do. I want you to be aware of what exists, and now if you want to, you can read that section of the chapter. I'm happy to meet with you. If you want to do some problems on that instead of some of the other problems I've assigned, I'm happy to swap problems around. But again, in the real world, you're not going to be doing these calculations by hand. You will have some package, and all you need to know is we can handle quadratic constraints if this matrix C is of a very special form, if it's positive definite. So the question is, how many of you remember what a positive definite matrix is? So this is linear algebra, which sadly this part is often not covered in great detail. What we mean by positive definite is that x transpose Cx is non-negative. And in fact, so C is positive definite if x transpose Cx is greater than or equal to 0 and is 0 if and only if x equals the 0 vector. You choose x to be the 0 vector, not surprisingly, x transpose Cx is going to be 0. This is used all the time in various things. If you do multidimensional Taylor series, you would get f of x is f of x naught plus the gradient of f at x naught, x minus x naught, plus 1/2 x minus x naught transpose the Hessian matrix at x naught, x minus x naught, plus dot, 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 dot. When you're trying to understand, do you have a maximum or minimum? In multivariable calculus, it's hell. They give you the equations. If the second derivative is positive and this product of partial derivatives is positive, then you have a minimum. If you can interpret this as a positive definite matrix, let's say you're at a critical point. At a critical point, this is 0 at a critical point. If you have a positive definite matrix, this means that this is non-negative as long as x is not x naught. If it's non-negative, that means you move a little bit away from x naught, your function got larger. So now you have a very simple test for maximum or minimum. If you have a positive definite matrix for the Hessian, then you have a local minimum. So this is one of the implications, one of the reasons why we care so much about positive definite matrices. They're the same, yeah. All right, so this is a good place to stop. I will send you some reading for the traveling salesman problem for next Friday's class. If you haven't sent me